embarking on a critical examination of the fractional quantum Hall effect, authored by Robert B. Laughlin, Horst L. Störmer, and Daniel C. Tsui in 1998, necessitates a journey into the heart of condensed matter physics. This essay will dissect the core claims advanced within this seminal work, evaluating their internal consistency, evidentiary support, and lasting implications. It aims to provide a comprehensive assessment suitable for an audience possessing a strong foundation in physics, including professional researchers, doctoral candidates, professors, historians of science, and advanced undergraduates. We will proceed systematically, addressing each section's core arguments and their justifications, while remaining faithful to the spirit and precision of the original text, albeit rendered in fully articulated language. Section 1: Introduction to the Phenomenon and Theoretical Challenges. The initial segment of the work introduces the fractional quantum Hall effect, observed in two-dimensional electron systems subjected to strong magnetic fields and low temperatures. It establishes the fundamental puzzle, the Hall conductance, a measure of the voltage induced perpendicular to an applied current, exhibits plateaus at fractional values of E² divided by h, where E represents the electron charge and h is Planck's constant. This is perplexing, because the integer quantum Hall effect has a straightforward explanation. A conductance plateaus correspond to integer fillings of Landau levels, essentially quantized energy levels arising from the magnetic field. The observation of fractional plateaus implies the existence of entirely new quantum states of matter, ones with fractionally charged excitations. Laughlin, Störmer, and Tsui emphasize the inadequacy of single-particle theories to explain this phenomenon, necessitating a framework that accounts for strong electron-electron interactions. The challenge, as they posit, lies in understanding how these interactions conspire to produce such remarkably stable and precisely quantized fractional values for the Hall conductance. This initial articulation of the problem is pivotal, framing the subsequent theoretical development. Section 2: The Laughlin wave function and its properties. A core claim of the paper revolves around the introduction and justification of the Laughlin wave function. This section explicitly proposes a trial wave function, mathematically expressed as a product over all pairs of electron coordinates, where each term involves the exponential of a complex number representing the difference between the coordinates raised to an odd integer power, typically 3 for the 1/3 filling factor. The power of this function lies in its answer that it embodies the idea that the electrons condense into a strongly correlated state, avoiding each other due to the Coulomb repulsion. This avoidance is enforced by the high power of the coordinate difference, creating a correlation hole around each electron. The authors argue that this wave function captures the essential physics of the fractional quantum Hall ground state. They present arguments based on variational calculations and plasma analogy to support this claim. Importantly, they demonstrate that the Laughlin wave function minimizes the Coulomb energy for a system of electrons to specific fractional filling factor. The discussion includes the concept of a plasma analogy, where the squared modulus of the wave function is interpreted as a Gibbs distribution for a classical one-component plasma. This analogy offers a powerful way to understand the stability of the Laughlin state, as the plasma is known to be stable at certain densities corresponding to the fractional filling factors. The strength of this section lies in the bold proposition of a relatively simple wave function that, nonetheless, captures the essential physics of a complex man-body problem. However, one must acknowledge that this is a trial wave function, and its validity relies on the strength of the supporting arguments and its agreement with experimental observations and numerical simulations. Section 3: Quasi-particles and fractional charge. This section delves into the concept of quasi-particles, specifically quasi-holes and quasi-electrons, as excitations of the Laughlin state. The work postulates that these excitations possess fractional charge precisely equal to a fraction of the electron charge. This is a revolutionary claim, fundamentally challenging the conventional understanding of charge quantization. To support this assertion, the authors introduce modifications to the Laughlin wave function that describe the presence of these quasi-particles. The key insight is that creating a quasi-hole effectively removes a fraction of an electron from the system, while creating a quasi-electron adds a fraction of an electron. The authors provide a detailed mathematical description of these quasi-particle wave functions and argue that they represent energetically favorable excitations. They also address the issue of statistics, suggesting that these quasi-particles obey fractional statistics, neither purely bosonic nor purely fermionic, but rather anyonic. This is another profound departure from conventional physics, as it implies that exchange into quasi-particles leads to a phase shift that is neither zero nor pi. The support for fractional charge stems from the topology of the Laughlin state and the incompressibility of the electron fluid. Specifically, the authors demonstrate that adiabatically inserting a flux quantum generates a quasi-particle, implying that the charge of the quasi-particle is precisely equal to the amount of charge displaced by the insertion of flux. This section's claim of fractional charge is perhaps the most striking and unconventional of the entire work, requiring careful consideration of the theoretical framework and experimental evidence. Section 4 Hierarchy of fractional quantum halls, recognizing that the Laughlin state only accounts for a limited set of fractional filling factors, those with odd denominators. The paper extends the theory to explain other observed fractions through a hierarchical construction. This section proposes that the quasi-particles themselves can condense into new Laughlin-like states, giving rise to a cascade of fractional quantum Hall effects. The argument begins by treating the quasi-particles as effective particles interacting with each other at sufficiently low temperatures. These effective particles can form their own condensed states, described by wave functions analogous to the Laughlin wave function. This hierarchical scheme allows for the explanation of a much larger set of observed fractional filling factors. The authors acknowledge that this hierarchical construction is not without its limitations. It becomes increasingly complex to calculate the properties of states at high levels of the hierarchy. Nevertheless, they posit that it provides a plausible explanation for the observed experimental data. The strength of this section lies in its ability to expand the theoretical framework beyond the initial Laughlin state, addressing a wider range of experimental observations. However, its complexity and the increasing uncertainty at higher levels of the hierarchy represent a potential weakness. Section 5 Experimental Verification and Challenges. This section addresses the experimental evidence supporting the theoretical framework presented in the previous sections. The authors discuss several key experimental observations, including direct measurements of the fractional charge of quasi-particles through shot noise experiments, thermodynamic measurements, probing the energy gap of the fractional quantum Hall states, and transport measurements, revealing the anyonic statistics of the quasi-particles. They acknowledge that some experimental results are not fully consistent with the theoretical predictions, highlighting potential areas for future research. The discussion on shot noise is particularly crucial. Shot noise refers to the fluctuations in electrical current due to the discrete nature of charge carriers. By measuring the shot noise in a fractional quantum Hall system, it is possible to directly determine the charge of the quasi-particles. The experimental results, while not always perfectly precise, generally support the theoretical prediction of fractional charge. However, the authors also acknowledge that interpreting shot noise experiments can be challenging, requiring careful consideration of various factors such as temperature and disorder. The discussion on energy gaps focuses on the energy required to create quasi-particle excitations. The size of this energy gap is a measure of the stability of the fractional quantum Hall state. Experimental measurements of the energy gap provide valuable information about the strength of the electron-electron interactions and the validity of the theoretical model. This section's reliance on experimental verification bolsters the overall argument, but it also reveals areas where The theoretical framework requires further refinement and more precise experimental validation. Section 6 Edge States and Chiral-Luttinger Liquid Theory. The paper then shifts its focus to the edge states of the fractional quantum Hall system. These edge states are one-dimensional conducting channels that exist at the boundary of the two-dimensional electron system. The authors argue that these edge states are fundamentally different from those in the integer quantum Hall effect due to the presence of interactions. They propose that these edge states can be described by a Chiral-Luttinger liquid theory. Chiral-Luttinger liquid theory is a theoretical framework for describing one-dimensional interacting electron systems. It predicts a number of unusual properties, such as the separation of charge and spin, and power law correlations. The authors suggest that the edge states of the fractional quantum Hall system exhibit similar properties. Specifically, they predict a tunneling exponent that is different from that in the integer quantum Hall effect, reflecting the fractional charge of the quasi-particles. The significance of this section lies in its exploration of the connection between the bulk properties of the fractional quantum Hall system and the properties of its edge states. The Chiral-Luttinger liquid theory provides a powerful tool for understanding the behavior of these edge states and their role in transport phenomena. Section 7 Composite Fermions and an Alternative Perspective. An alternative, complementary perspective is presented through the concept of composite fermions. The paper posits that electrons in the fractional quantum Hall regime can be viewed as bound states of electrons and an even number of magnetic flux quanta. These composite fermions effectively experience a reduced magnetic field and can form integer quantum Hall states at fractional filling factors. This section provides a different way to understand the fractional quantum Hall effect, focusing on the formation of composite particles rather than the condensation of electrons into a Laughlin-like state. The composite fermion picture offers a more intuitive explanation for certain experimental observations, such as the existence of particle-Hall symmetry. The authors emphasize that the composite fermion picture and the Laughlin picture are not mutually exclusive, but rather complementary descriptions of the same physical phenomenon. They argue that both perspectives are useful for understanding different aspects of the fractional quantum Hall effect. Section 8 Disorder and its Effects. The impact of disorder, inevitably presenting real materials, on the fractional quantum Hall effect is then addressed. The authors acknowledge that disorder can significantly complicate the theoretical picture. They discuss how disorder can lead to the localization of electrons, which can disrupt the formation of the Laughlin state. However, they also note that the fractional quantum Hall effect is remarkably robust against disorder, suggesting that the correlations between electrons are strong enough to overcome the effects of weak disorder. They explore the role of disorder in determining the width of the Hall plateaus and the sharpness of the transitions between different fractional quantum Hall states. This section presents a more realistic perspective on the fractional quantum Hall effect, acknowledging the limitations of the idealized theoretical models and the importance of considering the effects of disorder. It highlights the ongoing challenges in understanding the interplay between disorder and electron-electron interactions in these complex systems. Section 9 Beyond the One-Third State and Ongoing Research. The final substantive section delves into the exploration of more complex, fractional quantum Hall states beyond the one-third filling factor, and outlines directions for future research. The authors discuss the challenges in understanding these more complex states, highlighting the need for more sophisticated theoretical tools and experimental techniques. They mention the emerging interest in non-abelian fractional quantum Hall states, which are predicted to exhibit even more exotic properties, such as the existence of Majorana fermions. These non-abelian states are particularly relevant for topological quantum computation, as they potentially offer a robust way to store and manipulate quantum information. The section concludes by emphasizing the continuing importance of the fractional quantum Hall effect as a testing ground for fundamental theories of condensed matter physics, and as a potential platform for future technological applications. Section 10 Historical Reception and Subsequent Developments. The impact of the work on the scientific community is undeniable. The Laughlin wave function, the concept of fractional charge, and the hierarchical construction revolutionized the understanding of strongly correlated electron systems. The Nobel Prize awarded to Laughlin, Störmer, and Tsui in 1998 solidified the significance of their contribution, and the work continues to inspire research in condensed matter physics. However, the authors faced initial skepticism, especially regarding the notion of fractional charge. The experimental verification of this concept through shot noise measurements was a crucial turning point. Subsequent developments have built upon the foundation laid by this work. The composite fermion theory has become a dominant paradigm for understanding the fractional quantum Hall effect, and the search for non-abelian, fractional quantum Hall states remains an active area of research. Moreover, the concepts and techniques developed in the study of the fractional quantum Hall effect have found applications in other areas of physics, such as topological insulators and unconventional superconductors. Conclusion: the fractional quantum Hall effect by Laughlin, Störmer, and Tsui represents a watershed moment in condensed matter physics. Their work provides a theoretical framework for understanding a profoundly fascinating phenomenon that defies conventional wisdom. While the Laughlin wave function may be an ansatz, it is an ansatz of extraordinary power and insight. The concept of fractional charge, initially met with skepticism, has become a cornerstone of modern physics. The hierarchical construction, while complex, provides a plausible explanation for a wide range of experimental observations. The authors acknowledge the limitations of their theory, the challenges posed by disorder, and the ongoing need for further research. Nevertheless, their work stands as a testament to the power of theoretical physics to illuminate the mysteries of the quantum world. Its enduring significance lies not only in its explanation of the fractional quantum Hall effect, but also in its broader impact on the understanding of strongly correlated electron systems and its inspiration for new avenues of research. The boldness of the claims, the elegance of the theoretical framework, and the persistent experimental validation have cemented its place as a landmark achievement in the history of physics. Despite certain critiques and areas necessitating refinement, the work's central claims stand as a profound contribution to our understanding of emergent phenomena in condensed matter physics.